Voilà. Thank you very much. That's it.
Okay. So yes, we can start. As for this, I can leave it for the people presenting, right?
The way when you unmute it, it should be ready.
Okay. So just a reminder for all the presenter, you have like the keyboard here to move the slides. Forward is not the best option, but you can press the keyboard in normal presentation. So I'll start with the first one, that it's a video from one of the online presenter.
Hi, this is Jung-Seok, and I'm going to introduce a motion capture studio for creators. Motivation of our research is to generate natural and cost-efficient motion capture so that user can freely use it by replacing current high-cost motion capture system. We use full Kinect and a simple interface to accomplish our goal. The pipeline has three main components. It has a spatial refinement, which determines the reliability of joint using depth map. Triangulation, which maps from the multiple 2D joint to corresponding 3D joint. And temporal refinement, which reduces noise and outlier. In the result, we found that the variance of the scene and forearm bones from all sequence was reduced by about 64%. It can be considered that it produces a more reliable and plausible result. You can see the result in the video. The top left figure shows the depth map and confidence level of the joint with different colors. In the middle, you can see the more natural result compared to the 3D joint from all Kinect camera. As always, feel free to ask about questions.
Perfect. Let's move on.
Hi, this is...
Not again. So you can go. If you want this microphone, the one, as you prefer.
Okay. So I'm Martin Dornier, PhD student in Interdigital. I will briefly present my work improving self-supervised 3D face reconstruction with few-shot transfer learning. So the goal of 3D face reconstruction is to get a 3D face mesh from a 2D face image, but getting annotation for this task can be hard. And in the case of self-supervised methods that do not need annotated data, they tend to predict wrong face pose on scale. So our goal was to improve the predicted face pose on scale for self-supervised method, but use as few as possible annotated data. So our method has two stages. So first stage, we use a transfer learning to train a PNCC predictor with limited annotated data. And then we had the PNCC as additional input to a self-supervised 3D face reconstruction method to help it predict a better face pose on scale. So if you want more information, you can check my poster. Thank you.
Thank you. Next.
Do I need to do something here?
Yeah, you can just switch, so they know which one are the new, and then you can start. You have to move.
Hi, my name is Partridge, and our task here is to build a tool that allows for easy editing of facial motion. To that end, we try to learn dynamics in a way that allows editing to be intuitive. The problem that arises is that naive approaches will learn embedding vectors that have no semantic interpretation. So here we learn a disentangled representation, an unmixed vector, if you will. This allows for easy editing, as you can see. But it is also important that the disentangled vectors are still expressive enough to render natural motion. Please come and see this for yourself with our interactive demonstration. Thanks.
You can do applause between one and the other. So. You can go with this. Yes.
Hi, yeah, my name is Donal Egan. So our poster is a summary of our paper on virtual reality quadruped embodiment that we presented earlier this year at SEA. So basically the motivation behind it is that when animal avatars are available in VR applications, they're typically animated via inverse kinematics. This results in like unrealistic animations for the animal type, and this could potentially lead to a weaker embodiment experience for users. So basically, towards this, we developed NeuroDog, which is a VR quadruped embodiment system that uses deep learning to synthesize realistic motions for the virtual quadruped based on the user's input. So basically, the architecture is designed to preserve the synchrony between the user's front legs, or the user's legs and the quadruped's front legs. Yeah, and so here's some video results for the rest of my minute. Yeah, obviously more details are in the poster and the paper.
Just with the arrow, you can finish all the time. As you prefer.
Hi, my name is Bharat Vyas. I'm a PhD candidate at Trinity College Dublin. Yeah, the paper. So the title is Shapeverse, which is physics-based characters with different body shapes. The main motivation here is just because in humans we are different shapes and sizes, and it affects how we move. So we want to create the same effect, but we can't just capture, like do motion capture on everyone and like all the time. Also, we want we're working here with physics-based characters because they are more responsive and realistic. Like they generate more responsive and realistic motions. There are some details, but yeah, I can talk more in the posters. Like if you're more interested. But yeah, this is the basic framework, and these are some results. Yeah, thanks.
Which slide? This one, and you have the time here if you want.
So, hi everyone, my name is Julia Melgaré. I am a PhD student from Brazil. And the work that I'm presenting here at MIG, we basically wanted to ask ourselves, we wanted to answer two main research questions. So the first one, we wanted to know if a saliency model that is able to predict human visual attention on real images, whether it would work well in a stylized game-like environment. And the other question that we wanted to know is how does the user's degree of interaction with this environment can affect the amount of information that they understand from it. So in order to answer these two questions, we conducted a user study where we recorded their gaze data while they were navigating this stylized virtual environment. And we later compared their gaze data with the predictions of the saliency map for the same stimuli to see how well it would perform in this environment. And we also tested how two different types of navigations affected the user's behavior and understanding of the scene. So we actually had some pretty interesting results, and if you want to talk to me about them, I can explain to you on my poster.
Hello everyone, this poster is about a comparative evaluation of formed team perception when in human-human and human autonomous teams. In the existing perception studies involving AI teammates, focus have been on expectation, receptiveness, and others. In these studies, the participants are aware of their teammate being an autonomous agent. Therefore, these studies are heavily influenced by the participants' perceptual history of what they thought AA teammates were and their future expectations on how they are supposed to be. The contemporary literature does not address the evaluation of the already applied AI teammates when compared to a human teammate. Therefore, we propose a within-subject study with 2 sessions of dyads of human-human team and human AA team, with participants being unaware of who or what their teammates are. Thank you. Hello, everyone.
No hurry, no problem. So this one to move slides, and when you want, you can start it. Yeah.
So, hi guys, my name is Ricquebourg and I'm from Goldsmiths University of London. We want to understand how the different body function could shape the body control and body ownership. So we hypothesize that children under 10 years, they have wider windows of embodiment than adults. And we also want to know if the body function can constrain both body control and body ownership. So we implemented a linear gogo function, which you can extend your arm in super levels and sub levels, while maintaining the consistency of different max arm length gain. So we just for different participants do that. And also we developed a childlike gain, and which you can feed in animals by using the extend arms or shorten arms. So our current analysis shows that the VR experience has an impact on body control and body perception in real life. So we have already recruited 171 children for our study, and we are collecting some data from adults now. So please feel free to reach out to us via email, or you can scan our QR code to get more information. Thank you.
1 second if you want to take a picture of the QR code. So,
hello.
Yeah, you can move with the arrow in the space.
Cool. Okay, nice. I'm George Fletcher from the University of Bath, PhD student, and my work's on looking to improve motion matching for VR by using external pose estimation. So, the existing system I tried to improve. Motion matching for VR. The crux of the idea of this method is to predict the required body direction for motion matching from the headset signals, so these 3 sparse tracking signals. Found that that system had a limited sort of ability to generalize with its limited capacity, and so looked at using a sort of crude external pose estimator and fusing it with the existing signals, and evaluating the resulting error of the hip direction angle of the character and then the ground truth hip direction. Yeah, and feel free to come to my poster and have a look at these results.
Okay, so Mike, you have the time if you want to start.
How do I... Okay. Yeah. Hi, everyone. I'm going to show you how I enabled physical VR interaction with deep RL agents. So what I did is I integrated everything into the physics simulation, and which is the glue between the different systems, which makes it possible to interact bidirectionally between the two. If the video can work. Oh, yeah. Oh, maybe I should turn off the sound. So the first thing is we have retargeting for the VR, in the sense that if you hit a wall, an opposite force on the head will be applied. And in this case, with a lot of force and a lot of friction on the walls, you can simply swipe on the wall, which will make you jump in the opposite direction. In this case, you can, for example, grab the back of the RL agent and like ride on it. And in this case, you can also twist your hand to make it go forward, because it'll have to put a leg in front if it doesn't want to fall over, and you can turn it to change direction. This is just a design. This is not by design. This is just the systems that work this way. And here, this is my sister playing around with the RL agents, knocking them against the other. Thank you.
So if you want here, there is the time you can start, and then over with the harrow of this place.
Hello everyone. We are presenting today a work from the PhD studies of Theo Chenels, who unfortunately cannot be with us today. It's about motion retargeting, which is the fact to transfer a motion from one character to another with different morphologies. And it's called sparse motion semantics for contact-aware retargeting.
You can get your slides. I think
really?
Yes. There was one missing, but yeah, if you want.
Okay, so I'll just explain the main ideas. So basically, we have a sparse method that constructs sparse key points on a mesh, which allows to encode a motion in a sparse way. And doing that, we can easily optimize semantics from the source character to the target one. I know it's a bit abstract because you don't have illustrations, but doing so, we achieve state-of-the-art results in like motion transfer metrics, but also in contact preservation, which is pretty important and is a huge deal in retargeting. For example, when clapping hands, if you have different morphologies, for example, shorter arms or something like that, if a character is clapping hands, the source one, then the target one won't be actually touching his hands because he has shorter arms, right? So by encoding contacts, we actually achieve a retargeting method that encodes the contact. So it's a temporal method, it's state-of-the-art, and just go see the poster if you want illustrations.
If you have the slides, you can connect it after I don't know.
Why not? Maybe
if you want to show the illustration after, we can. So you can go just put the time if you want.
Okay. Hello everyone, so I'm going to present our work, Detailed HyeRin Capture and Animation, a novel HyeRin Capture Protocol, dataset, and robust HyeRin animation system. So our idea is basically to densely capture what we call the hypospace, which is the Cartesian product of the eyelid aperture and the gaze directions. And then we achieve one-to-one correspondence by skin and eyeball registration. And we can animate a person's eye by trilinear interpolation. And this is kind of an animation with our dedicated capture protocol, shows some good properties that I will explain in a short while in the poster session. Thank you.
Yes, time here to switch the slides for this place.
Hello, everyone. My name is Alberto Penina. We'll be presenting our work called Artworks via latent diffusion model. The idea behind this work is that we explore a creative technique for image and video generation. We want to add motion to static scenes, to static paintings, and we basically create a smooth transition between different artworks. We developed a method divided in 2 steps. The first one is a conceptual interpolation using diffusion models, where we generate K intermediate paintings between the real ones. And then we proceed with a tempo spatial interpolation between such frames using a film interpolation model. You can see here in this video some results. If you want to stop at my poster, I will give a bit more details on how this is done and maybe show some extra, more interesting results. Thank you very much.
Okay, so that's actually my poster. So I will present this pretty fast. So me and Pierre. So the work we want to do is to increase the realism of autonomous agent. That's a scene I want to show that is taken from an NVIDIA presentation for an AI for a non-playable character.
Hey Jen, how are you? Unfortunately, not so.
And so all the talks is generated automatically if I remove the audio. But what is weird in this scene is the environment. The environment is quiet. There is nobody. Typically, when you go inside the kitchen, you hear noise, you hear people. So what we think is just what happens in real life? When you have a communication, there are two people talking in a garden, you sometimes might have interference, like people burning stuff, make smoke, make noise, or cutting the grass. And so you might have interference in this communication. So what people typically do, they adapt. So they maybe speak louder, then repeat what they say, they move. So our idea is thinking of how this can be managed in games, for example. What we see nowadays, we see that typically when there is an important conversation, the games typically put the focus on the agent and blur out the rest. So you have focus there and you don't get distracted. But our idea is a little bit more complex. So we have our agent sending information, visual and sound information, so moving gesture and talking. And our user can be a VR user, any user receiving it. So what we do, we have this interference of the environment, noise, occlusion. And what we do, we try to analyze and compare what is the emitted signal in terms of feature and the received signal in terms of feature in order to have the agent able to react. So if you want to get more information on our idea and our proposal, please come to our poster. Thank you. Yeah, time if you want.
Okay, hi everybody. My name is Christopher Peters from KTH Stockholm. One of the typical ways that humans get together in an environment to converse and to collaborate is to form small groups in a shared space. So what we've been doing is conducting a series of studies investigating how these types of social interactions unfold when they involve artificial agents, such as virtual agents in VR environments and social robots in the physical world. This study, which was published in Eros last month, relates to two physical robots that invite a human participant to join their group using a variety of politeness behaviors. But there's a catch. The participant is invited into an inconvenient location in the group at a point furthest from their starting point in the study. So at this stage, they essentially have a dilemma. They could adhere to the request of the agent, but this involves effort. Alternatively, they could ignore its request and move to the closest position in the group. Finally, they might also adhere to the request of the robot and minimize effort by moving through the O space or the center of the group, but sometimes this can be considered rude. So the results of the study tells quite a bit about people's behavior in these situations, and I'm not going to tell you what that is because I'd like you to visit the poster. But one thing I can tell you is that the politeness behavior, we have identified a single behavior that achieves a good balance between gently persuading participants to move to a desired group position while also maintaining a positive impression of the robot.
Thank you very much. So my name is Mathias Delahaye. I'm a former PhD student from the EPFL. And during this PhD journey, I performed a user study that aimed to evaluate the approach that we implemented to retarget in real time one's motion onto avatars with different shapes and proportion. So the idea is that if I have a virtual body that differs from mine, if I directly apply the raw joint angles onto this 3D character, then this would lead with interpenetration. So that's why we perform this animation technique in real time that's also handled the finger level. So please pass by my poster if you want to have more detail about this. So thank you very much.